Here we go, it's recording. Great, so it's a pleasure to continue this marathon with Ernesto Lupercio, who'll speak on quantum toric geometry.
Well, as I was saying, it is a great pleasure to be here at this conference. It has such a festive flavor, and the talks have been great. And I hope that my talk connects to quite a few of them at different points. What we're going to do is we're going to talk about theoretic geometry, but a new flavor that we are proposing, Ludmil Katsarkov, Doran Merseman, and Alberto Verhovsky. And well, this is the paper. It's on the archive. It's called Quantum Toric Geometry, so it's easy to find. And so what we're going to do is we're going to take toric geometry and we're going to quantize it to deform toric geometry into a new realm. So this is the talk. This is all the talk, and this is the talk at a glance. So first, classical toric geometry. So what do we have in classical toric geometry? We have, I will do it over the complex numbers, of course. And so we have this complex torus of dimension d, C star cross C star cross C star cross C star cross C star. Complex torus of dimension d contains the real torus of dimension d. S1 cross 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 S1, etc. D times. And we have here the toric variety that is an let me think for this talk at a glance of toric varieties that are just compact. But of course, this not need be the case. So, and moreover, those that come from a polytope. But again, this need not be the case. In any case, we have this. And a toric variety will be this compact equivariant compactification of the complex torus of real dimension 2D, complex dimension D. And this real torus will act on the toric variety X in a Hamiltonian fashion. The toric variety is, well, in this case, it's everything. It's scalar, it's symplectic, it's complex. Because this real torus, this group, acts in a Hamiltonian fashion on the toric variety, just by the fact that, well, it's contained in the complex torus, then we have the moment map, and the moment map has this convex image, by Guillemin Sternberg or Atiyah or whatever. You have this convex image. But in this case, you have more, because it is a toric variety. The image is actually a polytope, whose dual is a triangulation of the sphere in RD. So it's a polytope inside d-dimensional Euclidean space. It comes together with an embedding. And combinatorially, it's the dual of a triangulation of the sphere, SD minus 1. So the dual would be a triangulation of SD minus 1. But it's more, not only is that, but it's also a rational polytope. So it actually lives on a lattice, because it has a finite number of vertices. So it actually lives on a lattice. So this is the classical situation. So we're going to quantize the classical situation to get quantum toric geometry. What does this mean? Well, in the quantum case, so what's going on? Well, quantum for us means that the spaces are going to be non-commutative. It will have a meaning in physics, quantum here. One can, just like here, you have classical mechanics to interpret this as an integrable system. You have classical mechanics. Here you have quantum mechanics to interpret this as a quantum integrable system. But even if you don't care very much at the moment about physics, you can think of it geometrically. And geometrically, it's the non-commutative geometry version of this is this. This is the non-commutative geometry. So here we have this Lagrangian tori as the inverse image of points in the polytope for the moment map. So here we have a quantum toric variety. We will have these quantum ones. They will also have fans and things like that. Quantum fans, quantum lattices, but let me not get ahead of myself. Anyway, there is this quantum moment map that realizes it as a quantum integrable system. And the image is still the dual of a triangulation of the sphere, SD minus 1. Combinatorially is the same, but if this is a bona fide non-commutative quantum toric variety, then the polytope it's irrational. And it's exactly rational in the classical commutative case, and it's exactly irrational in the non-commutative quantum case. So this is what a quantum toric variety affords you, is the ability to deform this polytope a little bit. You deform it with a little deformation h bar, you deform it a little bit, and then you get a new polytope deformed by h bar, and now it's an irrational polytope, and the inverse image of the moment map, it's a non-commutative space rather than a classical commutative space. So that's that. But now, you can deform not only a little bit. Notice that here, we have the combinatorics of the polytope. The polytope can be thought of as a combinatorial object. And here, it didn't change. The combinatorics is identical. It's the dual of a triangulation of a sphere. So the combinatorics is identical. What changed is that now you don't have quite a rational lattice here, but this is possibly irrational, and we have to account for that. And then you'll have this non-commutative space. But the combinatorics, we can fix the combinatorial type. We can fix a triangulation of the sphere, SD minus 1. And then we can turn on some non-commutative degree of freedom. I'll try to explain this. We turn on a gerb, and then we get MGN. MGN will be the modular space of quantum toric varieties. The MGN will be the modular space of quantum toric varieties. Actually, it should say quantum. Of course, the rational points of this modular space are the classical toric varieties. These are the classical toric varieties. So you still have the toric varieties, but of course, if you want to travel from a classical toric variety to another classical toric variety, fixing the combinatorics, fixing the triangulation of the sphere, the combinatorial type of the fan, if you fix the combinatorial type of the fan, and you want to travel from one quantum toric variety to another quantum toric variety, you'll have to go through non-commutative spaces to quantum toric varieties. In fact, there is a Teichmüller space here. There is a Teichmüller space that covers this. And moreover, this is a complex orbifold. This is a complex orbifold. So there is some technical term here. The calibration is the turning on of this degree of freedom. Let me just mention that there has been work in many fronts on the objects that you could associate to irrational fans from many points of view. And Hoffman, I should say here, Hoffman too. As I learned about his approach after I wrote this one. But anyway, Hoffman, in any case, there is 1, 2, 3, 4, 5, 6, 7, 8, and maybe more approaches to non-rational fans. And this is, well, another approach that it's very nice, in my opinion. What could I say? Because then you get this nice modular space. And now we have theorems that indicate that in favorable cases, stabilities, or whatever it should be called, you can compactify this modular space and get the compactification of the modular space. G is the combinatorial type of the fan, that's G. And N is like marking points in the classical case, corresponds here to marking a germ. It's also some sort of mark point, as you will see later on. It's also some sort of mark points. So if you have the right number of mark points, then you get the right situation in which you have a nice modular space, a nice orbifold, complex orbifold, and then you can do this modular space. And moreover, this compactification of the modular space. Let me stop 1 second and let me ask you if this is the talk. So now I will go on and on and on. But let me say if you understood what I just, if you have any questions or anything like that. Everything okay? Very well. I get a nice thumbs up. Okay. But here, let me go back here. And well, I need this. I need the tori. I need this tori, and I need this tori. I need complex and real tori, and because I will get, this will be a compactification, an equivariant compactification of a quantum complex torus. So I need the quantum torus, the non-commutative torus. To compactify it and for it to be Lagrangian, everything is made of tori. So my basic building block is the quantum torus. And now, this is the quantum torus. So remember, a non-commutative space, just the same space, you associate to it its algebra of regular functions, and you can associate the algebra to the space, and vice versa. To the algebra, you can associate the space, the variety, for example, and then, well, commutative algebras correspond to spaces. Well, roughly speaking, I should say here Morita equivalence and blah, 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 but I won't today. Roughly speaking, non-commutative spaces correspond to non-commutative algebras. Of course, you are to think, whimsically if you want, that the algebra of regular functions on a non-commutative space is a non-commutative algebra, where xy is not yx. And indeed, the quantum torus, whatever it is as a non-commutative space, is the algebra with two generators x and y, the quantum torus in dimension 2. It has two generators x and y, and yx is not xy. xy is yx times this complex number of modulus 1. For me, h bar will be my deformation parameter, and h bar will always be a real number. So this is always a complex number of modulus 1. And this is a non-commutative, slightly non-commutative. It's not horribly non-commutative. It's a non-commutative algebra. And this algebra appeared in the book of Hermann Weyl on quantum mechanics and group theory, and is the exponential of the classical Heisenberg-Jordan Max Born relation in classical quantum mechanics. But again, if you are going into the direction of quantum integral system, that's very relevant. But if you are going into the geometric direction, it's better to take an observation of Alan Kohn. And the observation is that this non-commutative space whose algebra of functions is given by this can be thought of as the space of leaves of a foliation, a holomorphic foliation, if you want. So what do you do to do this? Well, what you do is you take just the plane in this case, and you just take the integral lattice and form the torus, and you take all these parallel lines with a fixed slope h bar. The slope is h bar. H bar is the slope. So my deformation parameters is the slope of these lines, and is the h bar in physics. And so I take the quotient and I get this foliation called, very well known, Kronecker foliation. And of course, the h bar I can recover by going, if I take a transversal to the foliation, this vertical circle that crosses every leaf, then I start at a point of a leaf and I'll go about the leaf. And when I come back, I came back with a displacement. This is h bar, and this is the holonomy of the foliation. This h bar is the holonomy of the foliation. That's h bar. And well, it turns out that if you take this quotient, there is a dichotomy, an arithmetic dichotomy. It is a nice space. Hausdorff, it is rational, commutative, a nice space. It gives you a commutative space. In fact, if h bar is 0, this is just a commutative algebra. But H bar is not a rational. And if H bar is rational, this is confusing. Let me not do that in a second. Let me just think of irrational H bar. If H bar is irrational, then these leaps go, every leap goes out and about and about and about and about. And it's actually dense, of measure 0, but dense in the torus. But this is equivalent to taking the circle and rotating it by an irrational angle, H bar irrational. So all the information, you can recover the whole foliation by taking the circle and rotating it and gluing back like in a dent twist, but H bar. So H bar contains all the information of the foliation, or a rotation of the circle contains all the information of the foliation. So you have this foliation completely determined by H bar, and if H bar is irrational, it goes out and about, and the quotient is non-Hausdorff. And there is many ways to deal with non-Hausdorff spaces. One of them is to take the non-commutative space associated to the groupoid action. And the other one is to take the stack associated to the groupoid action. But in any case, Alan Kohn observed that if you take this foliation, this algebra can be thought of as the algebra of functions on the space of leaves of this foliation. This can be thought of as the algebra of functions on the space of leaves of this foliation. So, but this can be recovered, as I said, just from H bar. And in this very particular case, it is equivalent to take the stack associated to this quotient of this non-compact group on this compact manifold. So you get this non-compact group acting on this compact manifold, and you are going to use the exponential function. Because of the use of the exponential function, the stacks involved are non-algebraic and highly non-separated. But that's okay. We won't have a problem with that. So again, I can do it complex or real. I can do the complex version of this taking C star cross E star rather than S1 cross S1. Take it here C2 rather than R2. If I take C2 and I do the same, then I get the complex holomorphic Kronecker foliation, very simple linear foliation. And then, but the thing is, let's see the real case. Is the torus modulo this exponential action of the reals? The torus modulo this exponential that depends on H bar. That's the same as a quotient in the stack world as S1 modulo the rotation. S1 modulo the rotation. And by taking the Lie algebra, so to speak, the logarithm, this is exponential in the other direction. This is the same as R modulo the thing the additive subgroup generated by 1 and H bar. The additive subgroup generated by 1 and H bar. And this is what I will call, imagine that here you have the fun for P1, an arrow here and an arrow here. You have here the fun for P1. This is what I will need to make it quantum. I will call this a quantum lattice inside of R. This is a quantum lattice inside of the real line. And so R modulo the quantum lattice gives me the quantum torus. In dimension 2, observe kind of the displacement of dimension. This is a delicate point. So R modulo the quantum lattice will give me the quantum torus in dimension 2. So R1 modulo the quantum lattice. Imagine that H bar is the square root of 2, then well, you will have this thing is dense all over R. If H bar was square root of 2, this would be dense all over the place. And this is what you are meant to think for the truly non-commutative case. So this is an important model for us. Now, of course, I did in dimension 1, in this one. This is the picture for dimension 1, but I could do it in any dimension. And so if I take RD and I divide by a quantum lattice definition, quantum lattice is a finitely generated additive subgroup of RD. And if I have here square root of 2 and 3 and pi and things like that, Generically, this is a dense thing, the quantum lattice. And this plays the role of your classical lattice in toric geometry, this quantum lattice, this quantum lattice. So this one, the quantum lattice, and it plays the role in classical integrable systems of H bar. So the quantum lattice is H bar and is the lattice of toric geometry. This is the two analogies. This plays the role of H bar and of the lattice. In any case, this is the real torus, the real quantum torus, and this is the complex quantum torus. Definition, if you want. These are stacks. Stacks where, on what Grothendieck side? I'll tell you. But let me just, before I tell you that, let me give you the definition of a quantum toric P1. So a quantum toric stack will be an equivariant compactification of this quantum torus for a quantum lattice. Depends on the quantum lattice, of course. So, for example, take the quantum lattice 1H bar, this quantum lattice, this quantum torus, this complex quantum torus in dimension 1, this one, coming from the Kronecker foliation. All of them come from generalized Kronecker foliations, linear foliations. And think it's a square root of 2 if you want, and compactify it equivariantly, and this will be the quantum projective line. So how do you do the gluing? Well, the gluing is easy to do at the logarithmic level. Here you don't know. Here you don't know really what to do. Here it may be confusing, but here it's super easy because it's just, well, you just take this torus, and then you just take this torus. That is the same torus. It's an automorphism of the torus. And you take this automorphism of the torus. So just like classical toric geometry can be thought of as gluing one-sided compactified complex tori by automorphism of tori according to the instructions of the fan. The same is here, except that they are quantum tori. Quantum tori give me this automorphism, and then I glue this thing. I partially compactify it. This is the upper hemisphere. This is the lower hemisphere. This is the quantum lattice. And I get this quantum projective line depending on H bar. So this is a deformation of the classical projective line. And of course, as you deform, you get, when H bar is rational, you get orbifolds, you get footballs, you get things that have one singularity on top and one singularity, but finite, same mod P singularities, finite group singularities, when H bar is a rational number. But when H bar is not a rational number, you travel around non-commutative spaces, interpolating among different footballs, among different orbifolds. So that's the basic idea. So what is a quantum fan? Well, a quantum fan is the same. You know what is a quantum fan? It's a fan. But now it lives not inside of a classical lattice, but it lives inside a quantum lattice. Just a fan that lives inside a quantum lattice. But because now I cannot take the first primitive vector on this ray, I have to mark it. I have to mark these points. So I have to have these choices. And well, the quantum lattice could be this, or could have more generators. It doesn't necessarily have only these generators. It could have more generators. The case where it has only these generators is called gamma complete in our paper. It could be or could not be polytopal, the fan. It could be or not complete, the fan, but you know that. Or simplicial. But now it could be rational or irrational, the fan. And these lengths from here to here, and from here to here, and from here to here, and from here to here, just to tie in with quantum integrable systems, we will call them the Planck lengths. Usually in the universe there is one Planck length, but in these universes, these quantum mechanical systems were allowed to have many Planck lengths, many Planck lengths. So it could be polytopal or it could not be polytopal. So that's a quantum fan. So I'm, to one such quantum fan, I'm going to associate a stack over, that is going to be a quantum toric stack. To one such quantum file, I'm going to associate a stack over the side, the base category. The stacks will live over the base category of affine toric varieties. So the base category for my stacks is going to be affine toric varieties over the complex numbers with toric morphisms. Toric morphisms. And you could go back to non-commutative geometry by observing that there is a convolution functor of Alan-Kohn that goes from stacks to non-commutative algebras. But let me not say very much about that. In any case, A is a side. It has coverings in an obvious manner. You can cover something by Zariski open subsets that are affine toric varieties. The things that you are covering are affine toric varieties. If you take the category of complex analytic spaces, affine is there. Of course, not with less morphisms, just toric morphisms. And so I can take complex analytic spaces together with a holomorphic action of complex abelian Lie groups. This could be tori, but it could be non-compact. They could be non-compact groups. So this could be tori, but could have also kind of some sort of affine pieces. And so I'm going to take these complex analytic spaces with this Zariski open orbit. It's kind of generalizes these toric varieties. In any case, A is inside of this side. And what are quantum toric stacks? Well, whatever they are, they will have this form that I am about to describe. Quantum toric stacks are of the form, there is an ambulance coming by, are of the form X mod H. This is a category. So what is X, what is H? Okay, X is the recipient of a P equivariant, M equivariant morphism from the category A. And H is one of these groups that I had mentioned. Of course, I'm going to ask for these to be unramified and analytic, etc. In any case, all I'm saying is that the stacks that I was talking about can be thought of as stacks over A. And all the quantum toric varieties that I will have will be of the form X mod H. So they will be bona fide stacks over A. So this gets a little bit technical, so let me just do P1 because otherwise it gets too confusing. So again, P1, how can I realize from the fan of classical P1, you give me the fan of classical P1, and I have to give you one of these stacks over A. Well, so a stack over A will be a category. What will be the objects of this category? The object will be pairs of, this is T1 in A, affine toric varieties, to C, and T2 to C, corresponding to the two hemispheres of P1. So T1 and T2 give me a covering of T. So this will be an object of this category, T. Then M1 equals M2 equals C star. And all this is formal, nothing. The only content coming from the fan is this that tells me how to define the objects of this category. So the gluing, I use the gluing to define a bona fide stack over the category A. And then the morphisms, well, again, they are totally formal things. So this is the meat. And of course I could always realize all classical toric varieties as stacks over A. But the important thing is that there is more stacks over A than just the classical toric varieties. This is one, and this is a classical gluing, but there is more. And the quantum ones are here. The ones that compactify the quantum torus. Even just the quantum torus is here. So the quantum torus as a stack. Okay, I told you just symbolically or heuristically that the quantum torus was ZV mod gamma. and that the convolution functor by Kohn gives you this non-commutative algebra. But it can be seen as an object in this category of stacks over A. So I want it to be a category fibered in groupoids over A. So I get a gamma cover over A. Well, what is this? I'm going to get a T over A going to CD, M equivariant, and gamma acts on CD. So this is where the action of gamma is entering, forcing it to be M equivariant with respect to gamma. And then, well, the morphisms are totally formal, is what you would expect them to be. So the quantum torus is indeed stack over the category of affine toric varieties. Non-algebraic stack, totally non-algebraic, because these actions in the exponential situation are non-algebraic. We're using the exponential map. Observe that, though, I can unwind this definition that is elegant and formal and blah, 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 but into something extremely concrete. Essentially, I need this linear map that preserves quantum lattices, and that's the same as having one of these stack morphism of quantum tori. So I get a good category of quantum tori. But it becomes something extremely concrete. It becomes these linear maps. These linear maps are the same as the morphisms of stacks in this formal definition of category fibered on groupoids over A. In any case, an example is will clarify the situation. So let me get in dimension 1, the quantum torus here in dimension 1. In dimension 2, sorry, in dimension 2, remember that it was R1, and these were the quantum lattices. I was thinking of 1 square root of 2, H bar and H bar prime and then H bar. In that case, if this is H bar, and say I want to produce an automorphism to glue a new quantum toric variety from this one-dimensional T1, down here would be 1, and down here is 2, up here is 2. But it's what I need to glue one of these truly non-commutative P1s. Well, this linear, totally, clearly linear map, no mystery here, gives me this map that looks now mysteriously ramified. You know, the exponent is square root of 2, but everything has a meaning because of what I just said. Essentially, because of this diagram, everything has a meaning. So now I can glue W with W to the square root of 2 in this world, in this non-commutative world, and I can produce this new automorphism of this quantum torus because of the quasi-lattice was of high rank. Notice that is of rank 2 inside of R, the quantum lattice. Some people call it quasi-lattice, some people call it Q-lattice. I call it quantum lattice. Okay, so now we add just more letters and we do the same, and we get affine quantum toric stacks. So we get gamma, the quasi-lattice. The fan is going to live here. The fan is going to live here. This is the quantum lattice. It's going to live here actually, the quantum lattice. So let me think of a quantum lattice that is the classical lattice plus a deformation parameter, an H bar, a gamma 0. That has a square root of 2s and things like that. And then I exponentiate and I get this thing. And this thing acts here. And so this is, well, this could be CD minus K, but I might want to, because I took the classical lattice here, I can do this, because I have this periodicity of the exponential map. And then I can define it as a category fibered in groupoids over this site of affine toric varieties in the, well, what I have been saying all along. And so this, that as its quotient space, its topological quotient space, is all the time is non-Hausdorff. Its algebra of functions is a non-commutative algebra. Its algebra of regular functions is a non-commutative algebra. But as a stack is this stack. And it just, I mean, you can do it extremely concretely. So what is a simplicial quantum toric stack? Well, I'm now going to glue. You give me a fan, and I'm going to glue affine quantum toric stacks to produce simplicial quantum toric stacks. And because I want to finish early and have a short talk, I'm going to spare you the details, but you give me the fan, and well, just you put it straight, straighten it out, then you get the affine quantum toric varieties for every maximal cone, and then you glue the affine quantum toric varieties by the, you know, the information of the fan. This is the gluing cocycle, and yeah, you glue the thing, and then you get the simplicial quantum toric stack. It is what you imagine it is. Well, again, it's what I just said. So you give me a fan in a quasi-lattice with the mark points on the one skeleton, and then I give you, if you give me this fan, this quantum fan, I give you this quantum toric stack by using the gluing instructions of the fan, and using the quasi-lattice, and using the stack over the side of affine toric varieties. So as an example, a little bit more elaborate example than I did, this is P1 again, but now I take a quantum lattice of rank 3 inside R1. Notice that now it's a huge lattice, 3-dimensional lattice inside R1. And it's okay. And then I do that, I do the instructions, I glue the thing, I glue this thing with this thing, Z goes to Z a to the minus 1. And then I start to get, well, if I was in the rational case, where A and B are rational, well, then I could get the weighted projective spaces, P, Q, Q, A, but with a complicated arithmetic condition, etc., etc. So it's what I promise you. I would get the weighted projective spaces, but I also get the non-commutative spaces interpolating. As I move A and I move B, this can be rational or irrational. Then I get stacks, and in the rational case, these stacks are known, but in the irrational case, they are new stacks that compactify the quantum torus. Which quantum torus? This quantum torus is the one being compactified. C mod gamma. That quantum torus is the one that is being compactified. In this case, because we have one more rank in the quantum lattice, we would have an algebra that has X, Y, and Z for the commutation relations. What happens for quantum P2? Now we have this fan. The fan is the same, but now notice that the ray could have an irrational direction because A and B could be irrational. And blah, 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 you do the gluings, you do the thing, you glue this one with this one, and this one with this one, and this one with this one. And now you get a quantum P2. But now fixing the combinatorics, you can get a modular space of quantum P2s. Because now you can move things around. You can move things around. Okay, so what about rational quantum P2s? Well, it is a nice puzzle to us that there is this elaborate number theory that tells you that you recover all the weighted projective spaces, but it's non-trivial that you recover all of them because you have to do this elementary, admittedly in this case, but not entirely trivial number theory to prove that all of them appear in the modular space. Kind of funny. Of course, the most symmetric point, the orbifold point of the modular space is A equals B equals -1, as you would expect from this picture. So that's the quantum P2. I recover the weighted projected space, but then you have more. You interpolate between all the weighted projected P2s. You have the intermediate points in the modular space. So what is turning on the gerb? Blah, 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 but essentially, turning on the gerb means, let me just say essentially what it means. Essentially means this. Essentially means that you choose generators for your quasi-lattice. Essentially means that you choose generators for your quasi-lattice. And I'm going to always think of it, after arranging by a group action if necessary, that this is the classical lattice plus a quantum deformation. So it's the identity matrix. N is presumably bigger than D. N is presumably bigger than D, bigger than or equal than D. It has to be. Could be bigger than D. And then the first D ones, I take just the identity matrix, is the classical toric geometry. This would be classical toric geometry. But then I add H bar, taking the N minus D generators here, canonical ones, to N minus D generators here. And of course, it could be that this is not really generators. It could be that it's really more than generators, that you got redundant information here. And I want to remember that these things that do nothing to generate gamma, I also want to remember that information. And this is like marking points in the fan. This is like marking points in the fan. In some cones of the fan. This is like marking points. This is turning on the gerb or calibrating the fan or marking points so that my modular space becomes nice. And it's also nice from the point of view of physics, in which you get toric geometry plus H bar. H bar goes from Z to the N minus D to RD. So that's that. A calibrated, say that you get a calibrated fan, not only a quantum fan. Well, what you get after you do the gluing procedure in the very same manner, carefully, is what is called a gerb over the quantum toric variety. So the result of marking points on the fan gives you a gerb with integral band, whatever that is. You can think of it as a torus bundle. This one is a torus bundle. You can think of it as a torus bundle. So by marking points, you get this, and you can recover this by just forgetting the markings. You can recover this one by just forgetting the markings, like in classical modular space theory. So that's that. So we have quantum geometric invariant theory. And quantum geometric invariant theory is achieved by let's take a calibrated quantum fan with mark points and everything. Then we do the so-called Gale transform that is in convex geometry. This is a well-known procedure, but we have to adjust it very, very carefully for our situation. And well, with the Gale transform, we obtain some duality map here. But the point is, let me state the theorem and then stress the point of the Gale transform. The point is that with the combinatorics of the fan, with just the combinatorics of the fan, we obtain this affine toric variety. And this is exactly the same as would happen in toric geometry, because it only uses the combinatorics of the fan. It uses nothing else. This is just the same open set that you get for the Cox ring or for whatever in the affine, in the classical toric varieties. But now, using the Gale transform, these ones are the result of the Gale transform, you get this action, this foliation on S, and if it was a rational thing, the fan was a rational fan, this would be the classical foliation by tori on this open set of Zn plus 1, and will give you the classical geometric invariant theory for classical toric varieties. But now the leaves of this foliation can go out and about in an irrational manner, densely in zones of S. And what we get is the following theorem that says that if you give me the fan together with the quantum lattice with the mark points, then I can get this action. And so I can get this foliation that is an action by a non-compact group, not by a torus, but by a non-compact group. It would be a torus if it was a rational situation, but now it's not a torus because it's not the rational situation. And this stack, given by the holonomy of this foliation, the stackification of the holonomy group of this foliation gives you the calibrated quantum toric. So this is the geometric invariant theory in the quantum case, quantum non-commutative geometric invariant theory. This is a non-commutative space that compactifies the non-commutative quantum torus. And this gives you the foliation that generates this non-commutative space. So that's the non-commutative geometric invariant theory. The non-calibrated case, well, I'm lying a little bit. The calibrated case remembers the group action, The non-calibrated case only remembers the foliation. The non-calibrated, the non-mark case only remembers the foliation, and it's truly the holonomy groupoid of the foliation. Here is the groupoid of the group action, the groupoid of the group action. But this is a subtlety. P1, well, what happens in P1? Well, if you go through the moves, you do this kind of tropical condition. You get this lattice that is of rank 3 inside R1, and so you mark it. Moreover, with 4 mark points. These are the mark points in R, in the fan. Then, and you do the thing. You are compactifying this quantum torus. That is the circle by 2 rotations, or the complex version of it. Then you glue, and then you get the quantum P1. You get this quantum P1. But how are you? So you get this quantum P1 gluing this with this, and using the exponential map. What I said before. But I want to do the modular space of these P1s. And so I fix the combinatorics of the fan, is the fan of the P1. And I fix the number of mark points, is the number of generators of gamma, but even the fictitious ones, is the rank of the lattice that I'm going to -1. The rank of the lattice -1 of this lattice, this one. It's far away, this one. And then I get one complex parameter for all the P1s. And this is a complex orbifold. So this is the modular space of P1s. I have this automorphism acting on the fans. And so this is how it acts on the lambda parameter that comes from the Gale transform. But observe that this is the A1 and the A2 of the Gale transform, and I magically add them into a complex numbers. And this is okay. So this gives me a complex orbifold. It magically acquires a complex structure. So it is a complex orbifold, the modular space of P1s, with 3 narc points, so to speak. The geometric invariant theory for P1 looks like this. And this is the introduction of the very important component that inspired all this work, that is the Lbm theory for Lopez de Medrano, Merseman, and Verhofsky. So what's the deal in this case? So we have P1, and we're going to deform it. So we put in on top of P1 the Hopf surface, and then we think of it as an elliptic fibration. So these are elliptic curves, but I'm not happy with the elliptic curve. I take the universal cover that is non-algebraic anymore. The story. I see it as a foliation by complex leaves that wind up on themselves, and I'm going to deform this foliation holomorphically. And these leaves are going to go all about the place, no longer being elliptic curves, but being copies of the complex plane. So, and this is the parameter, the correct holomorphic parameter. This is the correct holomorphic parameter that deforms the foliation, given by the Gale transform, the geometric invariant theory. So, well, I deform by that parameter, and there I get the quantum P1s. And well, I get this action. So the foliation in S lives somewhere above N, and the foliation in S becomes a foliation in N, a holomorphic foliation in N, as I promised. And P1 is the space of leaves of this foliation on this complex manifold, this Hopf surface. So P1 becomes the space of leaves of a holomorphic foliation on a Hopf surface. If A and B are rational, if A and B are 1, these are elliptic curves, and it becomes just this classical diagram with the Hopf surface above P1 and elliptic curves. But if they don't wind up on themselves, this becomes a non-commutative space. The quotient space of this by that foliation, it's non-Hausdorff. So I need to think of it as a non-commutative space. I still have a moment map, though. I still have a moment map. Okay, so that is that. There is a beautiful story. All this comes from Lbm Theory. Actually, this gives me the Hopf surface as a submanifold of CP3 as a C infinity embedding. Of course, not a holomorphic mapping, but a C infinity embedding as the intersection of quadrics given by the information of the fan. So this gives me as an intersection of quadrics, of real quadrics inside CP3. In any case, I get this. This is it's always a Hopf surface. It is always a Hopf surface, but it comes with different foliations as I move lambda. As I move lambda, it comes with different foliations, and n lambda is the Hopf surface together with its foliation associated to the parameter holomorphic parameter lambda. And for example, if I take this parameter lambda,
Ernesto, you should keep an eye on the time because you're just over.
Oh, really? My watch says otherwise. I'm so sorry.
It's okay.
Okay, sorry. I have a, well, I just explained everything I wanted with the example. So I have the moment map, and I have the general version of this for all toric varieties, not only P1. For all toric varieties, I get the same story, and then I can deform them. So you give me one toric variety, I can do the Gale transform, and I can produce the modular space, and it's a complex orbifold. And this is the case of P2. You can also do it, and you can compute the explicit modular space. And the whole thing goes for quantum toric varieties. You have all these flavors of the modular space. Let me just say to finish that that Antoine Boisbach has a new paper on the archive where he does the non-simplicial case. It's a beautiful paper. He's a student, doctoral student at Angers, and I recommend you to see his nice, new, beautiful paper on the non-simplicial case. And that's it.
Thank you very much. Do we have any quick questions? Or maybe because we're over time, or just any other questions you have, we can do in the chat. We thank you again.
Thank you so much. Thank you so much.
Stop the recording, and then we'll start again in 5 or 6 minutes. Thank you very much, Ernesto.